Specifically, we would like to know for the past 250 million years, the plate tectonics already changed a lot. Then how the monsoon, regional monsoon and the global monsoon changed together with the tectonics evolution. That's our key motivation. So here I first show you an animation about the continental evolution since Pangaea. So at the beginning, there was the supercontinent, we call that a Pangaea supercontinent. Then at about 170 MA, the supercontinent started breaking up. At 80 MA, the continents dispersed mostly into smaller pieces. Then the smaller pieces of continents started assembled after 80 MA. Then the large change of the continent distribution, how that can cause regional and global monsoons. Then we carry out 26 simulations using CESM 1.2. One simulation, that's equilibrium simulation, is not a transient simulation. For each simulation, that's for 10 million years. So totally we have 26 simulations. Our simulations are for with two steps. The first step, we use the lower resolution CESM as the T31 version. Then we use the SST from the lower resolution model to drive the high resolution HGCM, that's 1 degree by 1 degree. For the lower resolution model simulation, here are the parameters. We use the solar radiation started at 250 MA, that's 98% solar constant compared with the present time. The orbital parameters all are the same with the present day values. We use the dynamic vegetation module. All other atmospheric compositions are same as the pre-industry values. The paleogeography, that's a key point. We use the data from Scottish. Then there is one other key point for the simulations. That's how to constrain the simulation. Usually people would use the CO2 level to constrain simulation. Here, instead of using CO2 concentration, we use the reconstructed global mean surface temperature to constrain our simulation. So for the upper panel, we can see the blue line. That's the reconstructed global mean surface temperature by Scottish. Then for our 26 simulations, we try different CO2 levels to make our simulated global mean surface temperature approach to the reconstructed surface temperature. So the blue line is the reconstructed surface temperature. The red stars are the simulation values we have. We can see they are very consistent. The difference within 0.5 degree. So to get the temperatures, we set the CO2 levels as shown in the lower panel. So the highest CO2 level was at 240 MA, which is about 26 times of the pre-industry CO2 level. I need to point out that this is mainly due to the dynamic vegetation model. We found that the dynamic vegetation not very good. Simulated dynamic vegetation, not very great. That can lower the surface temperature by about 3 degrees. That means if we have good vegetation, the CO2 level can be dropped by about half. I will point out this later. So here is the animation for the 26 simulations about the monsoon region change. We can see the blue area, the green areas are for the monsoon regions, and the yellow areas are for the dry regions. We can also see that for the supercontinent, Pangaea supercontinent at 250 MA, we can see the mega monsoon called by Kuzbak. Then when the supercontinent break up into smaller pieces, the monsoon areas, particularly the land monsoon areas, become very, very small. I will show you later about this. We can look at those 3 plots. We compare the maps at 250, 80 MA, and the PI simulation. We can see that at 250 MA, the monsoon area really large. That's the mega monsoon. Then at 80 MA, the continents spread mostly. We can see the monsoon area becomes very small, particularly the land monsoon area, very, very small. Then for the PI, we can see the Asian monsoon area is really, really large. Then here I show the time series of the global monsoon area. Let's first look at the black line, that's a global monsoon, including ocean monsoon and land monsoon. We can see at the beginning, the monsoon area really large, then decreasing together with the continent breaking up. Then the minimum is at about 120 MA. Then increasing again, there is the second peak at 60 MA. Then slightly decreasing. That's the global monsoon area. Then if we look at the land monsoon, we can see the land monsoon area doesn't change very much until 170 MA, then decreased. Then after 80 MA, the land monsoon area increasing again, then decreased after 40 MA. The ocean monsoon area also decreasing together with the continent breaking up, then increasing at Cretaceous, then decreased after 60 MA. So that's the global monsoon area. Then we look at the global monsoon precipitation, we can clearly see a peak, a very big peak during Cretaceous between 100 MA to 80 MA. We can see the ocean monsoon has a peak almost similar to the global monsoon. The land monsoon has a peak at 120 MA. Then we can look at, that's a global monsoon. We can look at the regional monsoon, how the regional monsoon evolved from 250 million years ago to the present. We first look at the land monsoon area. We focus on the land monsoon. We can see at the beginning, at 250 MA, for the supercontinent, there were 3 regional monsoons. There are 2 in the northern hemisphere separated by the Pacific Ocean. there is one in the southern hemisphere. Then when the continent are breaking up, the Asian monsoon doesn't change, still remains. However, the North American monsoon and the North African monsoon separated at about 170 MA. The southern hemisphere, at the beginning, there is only one monsoon region. Then after 120 MA, because of the separation between South Americans and South African, then there are two monsoon regions. Then I think after 20 MA, we can see the Australian monsoon, because the Australian continent already shifted to the closer to the tropical region. We also found some peaks. We'll talk about that later. For the land monsoon precipitation, the Asian monsoon precipitation doesn't change very much. The most significant change is for the North American monsoon. There is a peak at about 80 MA. Then the southern hemisphere monsoon doesn't change very much, although there are some fluctuations. Then we can look at the regional monsoon. Why there are the peaks for the Asian monsoon? First, we look at we compare the monsoon region at 190 MA, 180, and 170 MA. We can see for 180 MA, the peak is due to this peninsula or northern China. That's just right. The good location is around the 30° north. So we can see the monsoon area really large. For either 190 MA or 170 MA, this peninsula were farther north. So the monsoon area quite small. So that's why there is the peak at 180 MA. Then the second peak for the Asian monsoon region, monsoon area, that's at 40 MA. We also can compare the three panels. One is 80, the middle one is 40 MA, the lower one is 30 MA. We can see at 40 MA, the Asian monsoon area really large. However, for either 80 MA or 30 MA, the monsoon area is smaller. That's because at 40 MA, the Indian continent are already combined with the Eurasia continent. However, the Tibetan plateau still not rising up yet. So that's why we can see so large ocean, the monsoon area over Asia. For North African monsoon, we can also see at 40 MA, the North African is still in the south of 30° north. So it's right. It's also at the right position. Then at 30 MA, the African continent keeps moving northward. So we can see the monsoon area. You can see start seeing the dry area, the monsoon area shrinking. Then we look at the southern hemisphere monsoon area. We can see at 210 MA, there was a very large monsoon area. However, for 250 MA or 170 MA, the monsoon areas are much smaller. That also means that if the continent has a big area and at the good position, then you would have a large monsoon area. Otherwise, the monsoon area should be small. Here, I wanted to show you why the North African monsoon precipitation strength has a peak at 80 MA. We can look at this. At 80 MA, the northwestern part of African continent, they are separated. At this time, at 80 MA, we can see the smaller piece here. So here, that's also because this small piece of continent is within the tropics. So the precipitation is much stronger than at other time. Okay, I already show you how the monsoon, regional monsoon and the global monsoon involved with the continental evolution. Here, we wanted to further quantify how the continent impacts on the monsoon regions and the precipitation. Here we use the 4 parameters. One is the continent fragmentation. We define that with the total coastline length divided by total continent area. So that can measure the separation of the breaking up of the continent. We can see the first monsoon area has a negative correlation with the continent fragmentation. The continent fragmentation has a peak at 80 MA. At that time, the monsoon area very small. That means if you have a smaller continents, the land sea contrast would not cause very large monsoon areas. So actually during all the Cretaceous time, the monsoon area very, very small. Then we can look at the mean continent latitude. That means where averagely where the continents located at. We can also find if a continent located at a higher latitude. Let's see, in the north of 35 degree north, or in the south of 30 degree south, then the monsoon area are smaller. Then for this parameter, that's a total monsoon area, how the monsoon area is correlated with the total continental area. We can also see if the total continental area is, if that's small, the monsoon area also small. Then the last parameter is the global mean surface temperature. We can see the correlation is very low. It's not significant. So that means the monsoon area is not significantly correlated with the global mean surface temperature. Then we can look at the correlations between land monsoon precipitation and the 4 parameters. Very good correlation between land monsoon precipitation with the continent fragmentation. We can see those 2 peaks just overlaps. The correlation is close to 0.8. Land monsoon precipitation also has a close correlation with the mean continental latitude. Then monsoon precipitation has a negative correlation with the total continental area. We can look at this. That means if you have smaller continents, you would have a stronger precipitation, monsoon precipitation. You will have a large continent. That's the supercontinent. We can see that here the supercontinent, the precipitation is really low. Also, the monsoon precipitation has no good correlation with global mean surface temperature. The correlation is very, very low. So I think finally, I would think the NCA model developed group would be interested in what kind of problems we have in the simulations. We found a very big problem, which is about the dynamic vegetation module. Here we compare the dynamic vegetation with the default vegetation in the PI simulation. We can look at the lower panels. This is the default vegetation. This is the dynamic vegetation. We run that for 6,000 years. We can see the vegetation coverage is really, really low. That can cause the global mean surface temperature. You can look at this number. It's about, if we use, for the PI simulation, if we use dynamic vegetation module, the global mean surface temperature is lower by about 2.5 degrees. That's the surface temperature. Then the precipitation also much lower. This volume is for the daily precipitation. If for the annual precipitation, it's about like 21 millimeter for 1 year. So the dynamic vegetation can cause about 21 millimeters lower precipitation. Here are the time series for dynamic vegetation. We plot the time series for the 6,000 years. We can see it's already reached equilibrium. However, we can see the vegetation coverage is really, really low. So here comes our conclusions. The first point is continent evolution has caused dramatic changes of global and regional monsoons since the Pangaea. The second point, the total monsoon area, that's the land monsoon area plus ocean monsoon area. So the total area was the smallest at 120 MA. And the ocean monsoon area was the smallest at 120 MA. Land monsoon area was the smallest at 80 MA when the continents dispersed mostly. Monsoon precipitation peaked over 100 to 80 MA when continents dispersed mostly. The fourth point is both monsoon area and precipitation are closely correlated with continent fragmentation, total area, and the mean latitude, but have no significant correlations with the global mean surface temperature. So that's what all I have. Thank you very much.
Thank you, Professor Hu, for a very interesting talk. We'll open up now to some questions. I know that Professor Hu has been answering some questions already in the chat, but does anyone have any further questions they would like to raise their hand and ask? Let's see what we have here. Oh, we have Christine Shields.
Yeah.
I don't think you've gotten a chance to answer my question in the chat, so I just thought I would ask it. Have you looked at the evolution of the worm pools in the oceans and SSTs at all during the various periods that you've looked at? One of the things that I've noticed in my research is that a lot of the monsoonal precipitation actually follows the worm pools. So I was just curious how you dealt with that. Thanks.
Thank you. We do look at the SST. Actually, we found the worm pool for example, at 250 MA, we have only one ocean, one continent. The ocean domain is really much, much wider than today's. However, the warm pool didn't move westward very much. Just slightly shift to west. Doesn't change very much. We're still working on that. We don't know what's going on.
I'll just follow up that. We did a set of experiments a number of years ago with this was an older version of the model where we played with the land masses in the Pangaea and the Permian period and showed that the monsoonal precipitation didn't change much if you remove the land peninsula. So, and you can see the warm pool shift depending on where your island barriers were. So it was definitely not what we were expecting. So anyway, so that's just a piece of information for you.
Yeah, we also did similar simulations. We removed the small islands or the peninsula. However, the warm pool still doesn't move very much. We are confused. We don't know why. We hope. We expect to see when you remove the peninsula, the warm pool would move westward. However, we didn't see that.
Okay. So yeah, we can take it offline if you like, but I can show you what we did to do that.
Sure. Thanks.
We have another question from Jean Zhu.
Thanks for the talk. I have a question regarding the topography. I think when people talk about monsoon, usually they will think about the role of topography, for example, the influence on jet stream. So have you looked into that in your simulation?
Not yet. For all the talk, we haven't talking about how the, for example, Tibet Plateau, how that can influence the monsoon. We will do that, but now we haven't focused on that. Basically, for this talk, we just focus on the land-sea contrast, or the continent distribution.
Thank you.
Okay, maybe we should move on to our next speaker, who is Takasumi Kurahashi Nakamura from the University of Bremen. He will be speaking on coupling of CESM 1.2 and a sediment diagenesis model called MEDUSA, MEDUSA. And I see he has let's see. Oh, you're muted, Takasumi. Let's see.
Okay, now you can hear me.
Yes.
Yes.
Thank you. And I hope you can see my screen on my slide well, and also the cursor.
Yes.
Right?
Yeah.
Okay. So first, I'd like to say a big thank you for this great opportunity. I've never been to ENACA, unfortunately, so I'm very happy to join you for the first time, even in this virtual way. So today, I will introduce a recent work of ours about the coupling of CESM and Medusa. And this, okay. The contents, the contents of this talk is mostly in line with the GMD paper on the same topic published in the last year. So this work was done in the framework of the parent project PARMOD, which is aiming at long time scale climate simulations, including biogeochemistry, from a glacial interglacial perspective. And having that goal, we introduced a process-based chemical sediment model for 3 reasons. First, we needed to have a model including slow processes from the marine carbon cycle point of view, and this means we needed an open system taking into account the transient evolution of total inventory of biogeochemical matter. For the second, we wanted to have model version sedimentary archives that can be directly compared with real archives, which will provide an additional benchmark of the model performance. And third, it is expected that the chemical reaction in the sediment can have some influence on the bottom water chemistry in the ocean. And we wanted to assess the magnitude of that influence by changing the lower boundary conditions for the ocean model. We used CESM 1.2 with a prognostic carbon cycle, also with the carbon isotope package by Yang et al. And this model has already an empirical treatment of sediment distribution processes. And we used the low resolution setting like this. And for the sediment model, we employed a Medusa developed by Guy Moonhoven. And this model has an explicit vertically resolved structure, and it can handle oxic and suboxic remineralization of organic matter. And this model has parameterized calcium carbonate and opal dissolution processes depending on the chemical composition of surrounding water. If I show you a schematic diagram showing 4 different sediment approaches ranging from the most simplest type A to the most complex type D. In this diagram, I don't go deeply into this diagram today, but in this diagram, the replacement of the sediment package sediment module corresponded to changing from type B to D. Okay, for the coupling from POP2, we took the solid particulate fluxes, bottom water chemistry and temperature, salinity, and depth information from POP2 and gave them into Medusa to drive this model. While from Medusa, the solute fluxes from dissolution is given back to POP2 like this. And the communication between these 2 models were done in an offline manner. That is to say, we kept 2 executables separate and exchanged necessary information between the models through files. And the 2 models were run sequentially, and that is, we drove one model based on the preceding model state of the other model. And we chose this offline coupling mainly for the manageability of model development and maintenance. But afterward, we also enjoyed another advantage of this offline coupling. For example, we could make sensitivity studies or parameter studies with regard to Medusa very, very easily by running it as a standalone model. Nevertheless, we needed a substantial amount of modification of the both models, including introducing new variables, making writing reading routines, unit conversion, and so on. And we also made a new coupling interface first for one-time coupling and followed by its automation by making a wrapper level routine to repeat it. Then we made a controlled experiment to compare the couple model with the original uncoupled model. And we took pre-industrial physical restart information from Shields et al. And also with the prescribed default ecosystem initial state. First, we made a model spin-up. The length of this spin-up is 200 years for the entire CSM, but we used for POP2, we used the depth-dependent time step up to 20 times. So for the very deep ocean, it corresponded to 4,000 years. Then we took the solid particulate flux and bottom water chemical composition from this run and gave them to Medusa, the sediment model, to make a spin-up for Medusa as long as 100,000 years. Then we moved on to the controlled experiment. One was the simple continuation of this spin-up run with uncoupled original model. And the length is 100 surface years, corresponding to 2,000 years for the very deep ocean. And the other one is, so we call this experiment XORG in this talk. And the other one is X-couple with a new couple model. And we took restart information for CESM from this spin-up and took Medusa restart, sediment restart from this, and then made a new run, couple run. And the communication between the two models happened 10 times during this simulation. Before I show you the results about sediment, first I show you the bulk or globally integrated quantities or properties of the ocean physical and biogeochemical state. It includes the AMOC stream function for the two experiments, for X-couple and for X-org, and export production, the global rain ratio, PCO2, and also the total inventories for some species for those two experiments. And expected from the characteristic timescale of the ocean and sediment interaction, in short, the outlines of the ocean state was hardly affected by the coupling in such a millennial timescale simulation. And based on this, I move on to the upper sediment properties. So we will focus on the weight fraction of each solid component as one of the most straightforward benchmark quantities in this study's context. So this plot shows the weight fraction for calcite for X-couple in X-org and for observation-based reconstruction data set. And for the weight fraction, for calcite weight fraction, you don't see very, very remarkable differences between the two experiments, and more or less both have a rough agreement with the reconstruction. And this means in X-org, the prescribed spatially constant lysocline depth method works quite well in this case, although the weight fraction is underestimated somewhat in the Atlantic. But I'm afraid it would be difficult to guarantee the same method or same lysocline depth will work sufficiently good also for another very different climate state. And from that viewpoint, it is expected that having a process-based sediment model would be more reliable also in another climate state. On the other hand, for the weight fraction of organic carbon or for opal, you will see the much more noticeable differences between the two experiments. And I would say in X-org, the weight fraction of organic carbon is significantly higher than the reconstruction. and more or less that is similar for the opal weight fraction. And those very remarkable differences came from the different degrees of preservation of those two species in the sediment. If I make two plots showing the ratio of barrier amount to the particulate flux to the ocean bottom for the organic carbon and for opal, and the ratio calculated by Medusa, the sediment model, are shown as these scatter plots for every horizontal grid cell. On the other hand, the ratio given by the original simple parameterization of CSM, it is like this solid lines here or here. So if organic carbon or opal occupies the most part of solid component in a region, in such a region, the differences in barrier ratio will lead to big differences in terms of the weight fraction. So in the last section of today's talk, I will show you the effects of the coupling on the bottom water chemistry. So as I told you, the bulk globally integrated quantities are hardly affected by the coupling, but still the effect on the local bottom water chemistry was not negligible. For example, if you look at the delta carbon 13 field, the differences between X couple and X org is like this, and it was as large as or larger than 0.2 per mil, even in the millennial time scale simulation. And that magnitude is not negligible in model data comparison in a paleo context. The reason for the differences are twofold: a direct mechanism and indirect mechanism. The direct mechanism is the change of concentration due to the different solid flux from the sediment, and that mechanism can explain the anomalies in these blue ovals, mainly in coastal regions. On the other hand, the indirect mechanism came from the feedback from the ocean physics. For example, this dipole anomalies in the red oval is caused by water mass displacement due to the ocean saturation changes. For example, for this red anomaly, if you see the velocity vector fields and the delta carbon 13 fields at the depth of 3,900 meter in X couple, and there is much weaker penetration of southern source water having low delta carbon 13 into the North Atlantic, so that we got the much higher delta carbon 13 here in the low latitude eastern part North Atlantic compared this, and this corresponded to the red anomalies, one of the dipoles. So here is a brief summary of the talk. So we developed a new coupling scheme between CESM 1.2 and Medusa. Thanks to the coupling, some upper sediment properties were much better reproduced, which will provide additional benchmark for the model performance. Interestingly, the coupling has non-negligible effects on the bottom water chemical composition, even at the millennial timescale. And it is expected that the dynamical calcium carbonate diagenesis modeling will contribute to better long-term simulations in the future. So this story is not a real scientific application yet, but we are making progress for the next stage gradually, but certainly. Thank you very much.
Thank you. Questions?
We do have, oh, there's one hand raised.
Yeah, Dan.
Sure. Thanks a lot, Takasumi. That's
Hi,
really
Dan.
interesting. Hi. I was wondering if this model handles any sediment transport on the seafloor, and if you're going to think about different like aeolian and fluvial inputs of particulate matter in different climates.
You were asking about the horizontal transport during sediment.
Yeah, that's right.
Oh, for the horizontal direction, the medusa for each horizontal grid cell is completely independent from each other in this framework. So I'm afraid I cannot answer to your question very exact way because we haven't tried anything about that. So I can't answer to it quantitatively.
Yeah, that's
but I think
I was just curious. I think you mentioned at the beginning, wouldn't it be nice to have kind of model analogs of sediments? And I guess I've talked with people who go out and get sediment cores, and they always are kind of looking for where these things are draped over seamounts and stuff. And they said, oh, maybe that's the problem for the modelers. So I was just wondering if that was something that had been incorporated here. But it's definitely a much more complicated problem. So
okay, so I have to admit I haven't thought much details about that issue. But first, I'm interested in the characteristic horizontal spatial scale for that issue. For example, and so this is just my personal speculation, but I'm wondering if it's a really big issue when we talk about very global sediment properties or not. I can imagine it can be very important when you look at the very local sediment structure or properties.
yeah, that could be very well. Yeah, that it doesn't matter for these larger scale things.
I do have a quick technical question, and that is, so how did you run the POP? Did you run it offline from the atmosphere, or did you accelerate the circulation within POP?
And so I used a so-called B component sets for CSM. So everything is coupled within CSM. And then would you please repeat the question?
Oh, the question was whether you run then the model just without the atmosphere, so just prescribed atmospheric fluxes, or whether you did accelerate the circulation within POP. There's a possibility to do that too.
I'm afraid I still don't get the point, but
I can send you the question in the chat and you may address that. Okay, good, thank you. We want to move on probably. Yeah, thank you. There's several questions also in the chat. Okay, thank you.
Already.
Yeah. Okay, should we move on then to our next talk by Altug Akisi, probably not pronouncing that correctly, from the University of Bern, who will be speaking on carbon isotope-enabled simulations with CESM2 at the University of Bern. current status and first results.
Hello, can you hear me?
Yes.
Can you see my screen?
Yes. It's yes.
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 Hi. Thank you for inviting me for this meeting. Thank you, Esther, for the nice invitation. I'm Altu Ekici. I'm a postdoc at University of Bern. I'm working with Fortunat Jos there, and we are mostly working on developing isotope models here in Bern. So here I'm going to give you a short talk about our recent developments, and the presentation will be on carbon isotope enabled simulations with CESM 2.1. Just a second. Yeah. So this is an ongoing work, and I'm going to tell you the current status, and I will show some first results. Yeah, so let's jump in then. So to give a short introduction, I didn't think I had to give this, but I think it's just, we can go away. So the carbon isotopes, more attention here is C13 and C14. We can use them for distinguishing natural and anthropogenic climate change. And also, since I'm invited to this meeting, I guess for paleoclimate studies, it's very important to have isotope information in the models. And the thing is that as a historically, I think isotope development has been long in the agenda for CESM, and recently there were some developments for CLM and POP. There are some nice developments. Isotopic information is now possible in CLM and POP, and actually CLM was from the University of Bern. They have developed in 2017, and Alexandra for the POP version, so it was possible. The problem here is that there was no isotopes in chem, so no fully coupled isotope experiments are possible. This is not good if you want to make a long simulation, if you want to see the full effect of the system. So this has always been like has to be prescribed or use some other data sets. And here, what we did for the developments, we took CSM 2.1.1 for this work, and we successfully now managed to extend chem with a new passive tracer for C13. This actually follows the existing CO2 routines. I mean, everything actually follows CO2, except it doesn't interact with any other particle, or this is not reactive. It's just for transport and to show that C13 can be coupled with the land and ocean. So the existing CLM and POP fluxes are now coupled to the new C13 tracer, and the lowermost atmospheric C13 is now sent to land and ocean, and on the other way, the CLM and POP, they already had these fluxes, and now they are being sent with the coupler to atmosphere, and the calculations are being done for every time step. And this is working pretty well now. So we are happy with the first results, and we start our experiments. So experiment setups. The one thing I guess we all know, couple simulations are expensive. And to spin up, especially with isotopes, takes a long time. So we had a gradual strategy for this. So we first run CLM and POP in standalone versions. So we spun them up for more than 1,000 years with the already existing C13 and C14 modules active. After this, we actually continued with the fully coupled simulation using the CLM and POP spun up states, and we gradually opened the atmospheric CO2 and C13, so we can actually have this fully coupled simulation. Just to mention here, all the simulations I'm going to show here are 1 degree resolution runs, which were very expensive. And just for this study, atmospheric C14 is always prescribed. We haven't used atmospheric C14 active in the atmosphere yet. With this code, I think there are some developments, but we haven't included it yet. So to give an overall representation of our experiment strategy, so that you see here, I think you can see my cursor. So the standalone versions, CLM and POP, we run them both more or less 1,500 years with active C13 and C14. And then we started the coupled phase. So we have 3 phases for the coupled run. In the first phase, we run it for 200 years with constant CO2 and constant C13. So here I should mention that the pre-industrial atmospheric C13 ratios are hard-coded as -6.6 to 1. So this is the accepted value. So here in the phase 1 and phase 2, we use atmospheric C13 as -6.6 to 1. And after 200 years of this constant CO2 and C13, we open the CO2. So now we have atmospherically dynamic CO2. And for another 500 years, we run the model, continue to spin up the same, and we let the atmospheric CO2 to equilibrate. And finally, in the phase 3, we open the atmospheric C13 prognostically, And now we have another 300 years with fully coupled atmospheric C13 simulation, I think for the first time in an Earth system model for 1 degree. So now I'm going to show some results from our control simulation. And this is going to be from the phase 3 stage. With the last 300 years, we are going to see year 700 to 1000 all the time. This is the phase 3 part. Yes. So let's start with the atmosphere. As we see in here, the CO2 is more or less around 290 ppm. And now the new 13 CO2 value that I have added is following the same pattern. The new C13 follows the CO2 dynamics, and they are around 3.2 per mil. And the resulting atmospheric delta values, here we see two values in the bigger plot. Blue is the surface and black is the average of all atmosphere. So here, compared to the previous value of minus 6.6 now with this 300 years of run, the trends are negligible. The changes are pretty stable compared to the prescribed value, and we can say it's reasonably small trends is giving us confidence that atmospheric C13 is not going or pushed away from positive or to negative too much, and this is somehow good for us to analyze the land and ocean afterwards. So we are content with this result, and we check the results for the land and the ocean parts after. So here I'm going to show some time series for the last 300 years of our run. Here we see delta 13C from vegetation, soil, upper ocean, and the lower ocean. And here we can see that delta 13C is pretty stable for vegetation, soil, and upper ocean. And the trends are not so high. We can see the stabilization happens mostly after year 800 or 850. And less than 0.1 per mil for last 100 years trend, which is quite acceptable for us. The thing is that the deeper ocean delta 13C is still not stabilized. I mean, this is more or less 2000 years of run. And even carbon is not just equilibrated, and with the isotopes, I think it's pretty hard for 2000-year run to have deeper ocean stabilized. So this is not unexpected. We just have to accept it this way. I can also show radiocarbon results here. So the same as the delta 13C. Here we see the vegetation, soil, and upper and lower oceans. Here we see that the vegetation is pretty stable. It's just in the soil, we have a positive bias. It is probably due to older soil parts in the Arctic area, especially the permafrost, I think. And for the ocean, the full ocean, we have a negative trend. And this is somehow will keep coming up in my next slides, that the older waters in the Pacific are not really getting younger at all. And this is somehow not very comparable to observations, but this is the model. This was also the same, I think, with POP2 from Alexandra's paper in 2015. So we see a negative trend in the ocean radiocarbon. If we look at the distribution in the land, so here upper lower we see the vegetation map, and lower we see the soil. So delta 13 is somehow following the C3, C4 plant distribution. This is expected, as the photosynthetic discrimination actually follows separately for these two different types of plants. And what we see is that there are lower delta 13C ratios around tropics and a bit higher values around subtropical areas. And comparatively, in the soil, we see a bit slightly higher values than vegetation. These are quite acceptable, and they are comparable to other studies with the land-only runs. And if we go more detail for the ocean, I have some other plots. So here we are going to compare the model with some observation. Here I'm using Ada et al. 2017 Oceanic C13 observational dataset. They have delta 13C below 200 meters to 5,000 meters in the oceans. And when we compare the profile of all the ocean with the global value, we see that the values go in the top 2.5 per mil to the bottom minus 0.3 per mil. And compared to observation, around 500 meters, we have good match, but it's obvious below 1000 meters, we have a negative bias. And this is mostly explained by different ocean basins, especially Pacific. So if you look at the Pacific version, here again, blue is the model and black is the observation. So just for the Pacific, we see the negative bias is a bit more pronounced, especially below 500 meters, we always have around 1 per mil negative bias in the Pacific. However, in the other ocean basins, in Indian and Atlantic oceans, we have better matches, especially in Atlantic. The model actually does pretty well. compared to observation. This is quite motivating us. And for the Southern Ocean, again, we have deep ocean negative bias for delta 13C. If we look spatially, actually, how these changes are being represented, here I show 3 maps. Again, ocean delta 13C, observation minus the model, which means the red areas here mean model is underestimating. So in the 500 meters, we see a mixed signal, like red and blue colors, like in the Northern Pacific is underestimated. However, in Indian Ocean, we have some overestimation in the surface. But when we go deeper and deeper in 1,000 meter and 3,000 meters, we see the general attitude of the ocean is underestimating the observations. So this again confirms us the idea that the delta 13C is not stabilizing the deep ocean, and this is still needs some more time for spin-up time, but for surface values, it is not a big problem. So we have seen for 500 meters, it is acceptable. Apart from delta 13C, if you look at the radiocarbon, we again see a bias. Here, I'm again showing a comparison to observation. Here we use GLODAP version 2 data, and we have the radiocarbon comparison for the global ocean basin. Here we see surface radiocarbon is pretty well matching. It's around -50, -60 per mil. But when you go deeper, we have more than 150 per mil difference. And this again is more pronounced in the Pacific basin. We can see there's more than 200 per mil difference in the deep Pacific. But again, the surface and the first 300 or 500 meters are pretty well matching for radiocarbon. It's just the deep ocean circulation is, I think, slower than the reality, and the old waters are getting even older, and we're actually losing much more bias here. So the same can be said for different ocean basins, for Indian, Atlantic, and the Southern Ocean. So we have, again, Atlantic is less problematic. We have less bias in the deeper Atlantic. However, in the Southern Ocean and the Indian Ocean, we have still visible and consistent negative biases. So it's a pity that I don't have the industrial runs yet. So this is all the control run. So this is spun up for more than 2,000 years, and this is comparable to pre-industrial state. At the moment, it's an ongoing job. I'm actually running the industrial runs, and this will be more interesting to see modern day comparisons. However, we have a site study we have done with our master student, Tobias Frischneck. We have analysis of industrial global excess radiocarbon budget. So we use the standalone land and ocean simulations, and we combine it with the estimates from Nagler and Levin for radiocarbon, and we use this full budget as comparison to what happened in the production rates in atmospheric radiocarbon. So this is a rather complicated plot. I'm going to go a bit more detail here. So this is the evolution of excess radiocarbon. So this is what happened after 1960s bomb experiments. The extra remaining radiocarbon in the atmosphere is being absorbed by land and ocean, and some of them is from stratosphere and troposphere. So what we do here, the green is the land industrial run offline, blue is the ocean industrial run, and for the atmosphere, we use estimates from Nagler and Levin. These are observationally inferred estimates. So totally, we have this purple line, the sum of land and ocean uptake plus the observation, compared to the productions from different sources from Young and Ralph. So here we see that first of all, in 1960s, the uptake totally is a bit lagged compared to observations. And then 1962, we have a bit overestimation. And afterwards, we have a consistent underestimation of the observational values. But again, the idea was to whether the land and ocean uptake is consistent with atmospheric production rates. It is still like 10% difference with the observational values. It's not so bad. So what I want to say here is that the blue boxes for the ocean are independent observations of ocean radiocarbon uptake. And here we see that the ocean model is not doing so bad. And the crosses here are from previous pop estimates from Yan et al. And we actually saw there's a difference between the forcing files. So since these are offline runs, we can force it with different atmospheric values. So the solid line for the blue here is actually coming from the Core 2 large and Jaeger data, normal year forcing. However, for the dashed line here, we use the Japanese reanalysis data, JRA. So we see a difference here, mainly because of the wind speeds. So since ocean uptake is pretty sensitive to the air-sea gas flags, and this is really related to the wind speeds, we actually see using the normal year forcing has better results. And when we see the comparison with the full budget, we actually see a better estimate, better matching with the observations. So this is something actually we should keep in mind, especially when we do offline runs, that the wind speed and the use of different atmospheric data actually have a big impact in the end. For land, I don't have an observational data here, but here we can show just for the CLM offline run. This is from the same study from Tobias Frischnecht. It's another plot. So here what I want to say is from 1850s to 2005, this is the excess radiocarbon. So the vegetation is shown in the green plot, a green line, and the total land, vegetation and soil, is shown in the black line. Here again, there's an observationally inferred data from Negler and Levin. We see the observation with the uncertainty. It is over the land estimates. So here we can see that the difference between the total land and the observational base is more or less 8 to 10 kilomole of difference. And this actually explains the difference we actually see here with our total estimate versus the observation. We actually do have 8 to 10 kilomole differences. So we can actually say this is probably the lower NPP of CLM that is lacking the radiocarbon uptake. Just to confirm this, we actually make another test or another observational analysis with the ocean. Here we compare the ocean data with the coral data sets. So corals from all around the ocean, there are different depths and different geographical locations. Here we see the lines are the ocean model data, and the points, the dotted lines, are from observation of corals. So we see actually POP is doing pretty well, capturing the radiocarbon uptake for different parts of the world and different depths of the ocean for different corals. So this actually confirms that POP2 is actually capable of representing this radiocarbon uptake. However, we have to say the general estimate of global radiocarbon excess budget is underestimated, which is probably due to NPP of land CLM model. Here I finished the presentation. I don't want to take too much of time. So what we wanted to say here in the end is atmospheric delta 13C is successfully coupled to ocean and land components. And we can proudly say the fully coupled C13 simulations can now be performed with CSM 2.1. So we can now start making industrial runs or even paleoclimate runs if anybody is interested. So my next steps will be to finish the industrial period run with land use change and C13 fossil fuel emissions. So I'm having some problems here with the land use change. This is going on. And afterwards, we will continue with factorial simulations with different scenarios. I stop here with my presentation. Just want to acknowledge my project and the people who has helped us. Thank you very much. And I'm happy to hear any questions. Thank you.
Thank you, Altug, for a very interesting talk on new developments. Questions? Raise hand, please.
I was wondering whether you have started to look actually in some of the variability. So for example, El Nino, Southern Oscillation. Would be actually interesting to compare that with previous estimate from Martin Hyman and Charles Keeling to see whether you see in your modeling also the signal. Since the model, I think, is now better producing ENSO variability, it may be worth the effort.
Yeah, I totally agree with you. I mean, we are still waiting for the industrial run to finish to actually have something more like a dynamic changing results to actually compare with the recent El Niños and the other observational data. But at the moment, we are still dealing with the industrial run. There are some issues came up and it's still going on. We are hopefully going to add that when we prepare the paper.
I have a question about how expensive is this run to produce? Is it it's a lot more tracers, especially with the ocean?
So technically, so we are running it here in Silverstone with the supercomputing center. I am using 60 nodes with how many? So what I have as a throughput, fully coupled run with the C14 on, I'm having 13 more simulation years per day.
Oh, okay.
My ideal setting.
And what resolution again are you
1
running?
degree.
1 degree. Oh, that's awesome. Yeah, that's pretty good. All right. If there are any other questions, maybe they can be asked in the chat. And I think, these 2 new developments talks that we heard, it would be great to, collaborate more, maybe check in with each other more just to find out what's happening with these different groups and the different developments, so we can ensure that eventually these get incorporated into future versions of CESM2. So thank you for presenting, both of you. So, all right, I guess we have a break now. We'll start back up again at 10. So about 15 minutes or so. I will see you all then.
Also, Altug, if you're still here, you're still sharing your screen. You're pulling a Hannah from yesterday, so.
Let's see. There we go.
So Sophia, do you want to test your screen sharing? Otherwise, I can start to put my screen sharing up.
Did you just speak to me?
Yes, yeah.
Oh, yes, okay. Oh, should I test my screen share?
Yeah, we have a little bit of time now. Yeah, that looks
We're
good.
good?
Yeah.
All right.
Okay, thank you.
Yeah.
Should I put the agenda up here?
Sure, and then maybe 5 minutes before, or 2 minutes, 2 to 3 minutes before I can put up my presentation.
Okay.
Esther, can you remove your sharing? Thank you.
Oh,
So you normally share the desktop, is that correct?
yep, share screen.
Okay.
And
I
then
have open system preference.
I'll do that. Do you see the share screen?
Yeah, I see the share screen and then I go to desktop.
Do you see the window? It worked for me if you sort of click the PowerPoint open and then
Okay.
share screen, and then you should see the window.
Okay, let me click there. So my PowerPoint is open.
But not on. Don't put it in the show mode. Just click it open and then share screen at the bottom. At least it's the bottom on my window.
PowerPoint, let's see. I think open, okay. Okay, oh, I need to do that, okay.
Do you see the window with your PowerPoint?
Yeah, I need to do, do I need to leave the meeting and then join again?
I don't think so.
Yeah, I think I need to allow the privacy on my, I haven't done that on Zoom, you know. So I need to.
Okay, we're waiting for Arnie to join back. Sophia, did you test out your slideshow sharing?
Yes, during the break, I practiced some sharing.
Okay. I stepped away. I thought Arnie was sharing his during the break. I guess not. Let's see if is he back? Not yet. Okay. Why don't I share my screen again till he's back. Let's see.
Can you remove your screen as Esther?
Yep, I will.
Yep.
Okay.
Okay. Okay, now let's go to the PowerPoint. Sure. Can you see it now?
Yeah. So now you just have to start it up.
Yeah. And then presenter mode and pointer, laser pointer. Okay, good.
Okay, our first talk after the break is by Arnie Winguth from University of Texas, Arlington, who will be speaking on marine productivity and dissolved oxygen changes at the PETM.
Thank you, Esther, for the introduction. So I want to talk here about the modeling work we are doing for the PETM, and we're focusing here on the carbon cycle changes. The physical changes I have presented in previous meeting. I want to acknowledge my co-authors, particularly the students working in my group, Jerry Wang, who run most of the carbon cycle simulations, and then James Breen and Michaela Brown, who helped in analyzing the results or providing some of the plots. I want to acknowledge my sponsors in support of that work. So the PETM is of great interest because it's one of the hyperthermal events at the late Paleocene, early Eocene. And it is known as global warming event of 4 to 6 degrees with high latitude warming even warmer than 15 degrees. The causes of the hyperthermal event, of this hyperthermal event, is still controversial discussed, but among favorite hypotheses are volcanism and carbon release from marine sediments in form of the methane hydrates or gas hydrates. It's also of interest because of large ecological changes on land and in the ocean. I want to focus here on those in the ocean. And there was a wide extinction of benthic foraminifera, shown here species which became extinct. And you see also signs on the foraminifera shells where the shell became degraded, and that's likely linked to ocean acidification. Shown here on the right is a record of the benthic forum extinction from Alan Thomas and Berggren. And of interest is mostly the extinction events in the Atlantic Ocean. So I want to focus on that. So as we heard in the yesterday's talk of Andreas Schmidtner, so of interest for the carbon cycle and also the oxygen in the ocean are two major pumps, which are, one is the solubility pump, so the fresher the ocean or the colder it is, the higher the solubility is. So this is here the reconstruction of the famous Weiss curve from 1970. And then shown here from Liz Griffiths in a paper we're currently is in review is then the biological soft tissue pump and where photosynthesis then generates then particular organic carbon. It's also created by grazers as in form of the fecal measures, and is also somehow decomposed by these grazers. And so the particular organic carbon flux rains then into the abyss, and so most of the remineralization takes place in the mesopelagic or twilight zone. As a product of these remineralization product is also the marine biret accumulation, which we find on the sediments, and so we can use that to reconstruct and paleoproductivity in the past. And so the forums are mostly depending on how much organic carbon is flowing to the into the sediments. So if there's too high organic carbon, then there may be anoxia and they may perish. If there's too low amount of carbon, they will then starve. Here are shown then the reconstructions on the left from the Marr paper based on the biret accumulation rates, and you see the pre-PTM condition is here significant increase in the productivity, particularly along the equatorial records, but also in the South Atlantic Ocean. In contrast, the modeling work we carried out together with Alan Thomas and my wife suggested that the productivity actually was significantly reduced. So it's in contrast to the data. So the question is, what causes this discrepancy? And what should note is that there may be either the increase in the productivity, but on the other hand, there could be also an increase in the reminerarization rate. And so we want to look now to CSM simulation to address that. So the next slide showing the barite accumulation rate. And so this is the PTM record, which we showed before, so pre-PTM and PTM. But before there were actually increase in the barite accumulation rate, and that actually nicely matches with the oligotrophic taxa, as I explained before. However, if we see this increase in barite accumulation rate at the PTM, we don't see these increase in oligotrophic taxa, but we see actually a larger extinction of the forum. So that's quite interesting. You see here the PTM onset with a negative carbon excursion, and also the increase in the temperature as revealed by the Dedo 18 oxygen record. So we're using here the CSM 1.2 simulation. We're using mostly the deep map conditions here to run the model. I've shown the physical part before. This is a 1 degree resolution pop, 2 degrees atmospheres we are running that. And the physical model we have run already 2000 years. So what's new here is now the carbon cycle simulation. And so these are at 1 degree ocean. So they're slowly progressing about 2 years per day or 4 years per day. So it takes a long time to integrate that. We're using a moderate amount of processors. But so we have done some progress here over time. And so the PI run is now mostly 2000 years integrated. Then we do have with BEC carbon cycle, we do have also the 1 times PTM run, so with 1 times so premenstrual CO2 radiative forcing, but Eocene boundary conditions otherwise is also 2000 years integrated. And then the 3 times CO2 run is 2000 years integrated, but JE and I had real problems with the 6 times CO2 run, because this is a hot house climate and stresses the BEC. And we had to work hard to get this run continued, so that led to the delay. So here shown the surface air temperature, you see this 6 times minus the 3 times CO2. So 3 times CO2 simulation matches quite well to the pre-PTM condition. The 6 times CO2 simulation matches to the PTM condition. Here shown a comparison with the data from Hollis 2019. You see general agreement, but you see some biases, particularly in the Arctic Ocean. If we want to reach that warm temperature in the Arctic Ocean, we would need much higher CO2 level, but that would contradict the data like from Foster et al. So for the carbon cycle, it's of course important to show the MOC. And so here we see a vigorous ventilation from around Antarctica, particularly in the Atlantic sector, where we have the deep water formation, and that penetrates then into the deep sea. And then we do have a shallower circulation from the North Atlantic in intermediate depths. So this deep sea circulation, which is ventilated from Antarctica, has been shown in previous paper from Mikulevich and Meyer-Reimer in paleooceanography. And so if we're increasing the CO2 radiative forcing, we see then a decrease in the deep sea ventilation around Antarctica, eventually stagnation of the deep sea circulation or collapse of the deep sea circulation. And also at really high CO2 levels, the Atlantic circulation decreases. And so we're seeing actually a change from the 3 to 6 time circulation in terms of the mode of the circulation. So this is a typical thermal mode, and then we are changing into a haline mode where we have deep water formation in the subtropics. I've shown that at the last annual meeting. So the changes in the productivity, so this is then the 6 times CO2 simulation. The general patterns are agreeable with the present day patterns and also that of Mar, where we see in high productivity along the equatorial region or in the Pacific and Atlantic, also the high latitudes, the subpolar region around 60 degrees, we have a high productivity due to strong mixing processes. And then we do have these oligotrophic region, which we have also in the present day ocean along the subtropics. Of interest is that we find here the similar patterns with a more complex CSM 1.2 than we found with CSM 3. So we see actually the reduced productivity at the equatorial upwelling belt. This is due to reducing the upwelling in this equatorial region. But noticeable changing to the CESM3, or for example, we see actually in higher productivity now in the South Atlantic. And so the reduction, the overall reduction we see here from the pre-PTM simulation, so 3 times CO2 to the 6 times CO2 simulation, which about 15% is due to this reduced upwelling and reduced mixing, and so reduced nutrient supply to the surface. Jai Wang looked also in her thesis as in the changes of the ecosystem dynamics, so I don't want to talk about that here. Now, the bottom water oxygen concentration is shown here in this graph, the 3 times CO2 simulation, the pre-PTM condition here, and then the PTM condition. So in general, the records indicate that we don't have anoxia during the PTM, and that's supported here by the simulation, but here shown the errors in terms of the ventilation strength, and we see actually lower oxygen concentration in the Atlantic and the South Atlantic compared to the pre-PTM condition. We're seeing also increased deoxygenation in the Pacific. So this is consistent with a previous analysis we see we have done with Andy Richwell comparing CCSM3 simulation with the Gini circulation. And so there's multiple processes related to the lower oxygen concentration. Of course, we do have the changes in the circulation, then the changes associated in the solubility pump because it's warmer, and then we do have the biological processes. I want to look more in detail here in the biological processes. In contrast to Andrea Schmidtner talk, we don't consider here the disequilibrium, consider changes in the oxygen concentration. So that may be a thing we may look into the future. But here's the oxygen concentration shown. So we do have well ventilation of the oxygen here into the abyssal ocean from the Weddell Sea mostly. And then we do have this high, low oxygen concentration below the productivity zone. This is mostly by decomposition, by remineralization of particular organic carbon in that layer, which consumes then the oxygen. Now, what we are using here is in order to estimate the biological effect is a apparent oxygen utilization, so the more classical approach, where we're using the O2 saturation minus the oxygen value to define the AOU as a difference between the idealized oxygen saturation, which depends just on temperature, pressure, and depth, minus that what we are simulating here, which includes also the biological component. So the AOU is somehow representing the biological pump, and what we see is here in the 3 times CO2 simulation, we see here these a high oxygen utilization due to the remineralization, and then the other values are relatively low, so this is a dominant part. So of interest is now, of course, the changes in between the different experiments, the 6 times CO2 minus the 3 times CO2, so which is the PTM minus pre-PTM conditions. And we're seeing here actually depletion of the oxygen concentration, mostly in the twilight zone. And so that is, so the question is whether that is due to the solubility or the biological process. And we see here as part of the apparent oxygen utilization that is mostly linked is linked to increased remineralization in the twilight zone. So we have then looked into a more simplified model simulation. That work has been done by Don Penman from Yale. And so he had done increased remineralization simulation with the LOSCA model. And so this show here about an 18% increased remineralization as inferred from the KPG boundary from cellular hole. The time scale is about that equivalent to the PTM recovery. And so you see that increase, and if that model now shows then that increase of export production in PCO2, but that model is of course not in the complexity of the CSM model. And so that's actually interesting to look in the future, what will be the difference. Now back to the foraminifera changes. So we don't see actually these oligotrophic conditions since we have an increased productivity, and we don't see the oligotrophic species. So for the PTM, we would favor then the eutrophic condition where then we have that enhanced rain of particular organic carbon to the seafloor would lead then eventually to the demise of some foraminifera species, because the sedimentary level become more anoxic. So I want to put up the conclusion because my time is over, and I want to, then I'm happy to take questions.
Questions for Arnie? Thank you for the nice talk, Arnie. Let me look here.
I have a quick question.
Yeah.
Thanks, Ernie, for the exciting talk. So I have a quick question regarding your simulation. So how many more years are you expecting to run the simulation?
Idealized for the carbon cycle, you would need to run 10,000 years and more, but that's not feasible. And so we can actually look on the trends and change it, and we're doing the time series, which I haven't done. And so typically we have shown that 2,500 years, 3,000 years are feasible. I think because of the cost and we are running out of computer time, I think 2,000 years is at least anticipated. And so we need to run 1,000 years further for the 6 times CO2 run.
Okay.
Yeah. Okay.
Let's see. I think we should maybe move on here. Do we have, well, we could, yeah. Further questions maybe for the chat, if anyone has any.
Sure, we'll look at.
Should I start sharing my screen now?
Sure.
Sure.
Okay. Oops, sorry. Okay. That's that. All right. All right. I'm good to start?
Sure. Yes. I think, okay, Arnie, Our next speaker is Sophia Makarewicz from the University of Michigan. Her title is Ocean Deoxygenation Linked to Abrupt Global Warming During the Earth's Penultimate Icehouse.
Yes. Hi. Yes, exactly. I'm Sophia Makarewicz. I'm a PhD candidate from the University of Michigan. And today I'm excited to present to you our work on ocean deoxygenation linked to abrupt global warming during the Earth's penultimate icehouse. So ocean deoxygenation is already an increasing problem today. Marine ecosystems are being strained by the loss of dissolved oxygen in the ocean. And this problem is expected to get worse as warming decreases the solubility of oxygen in the ocean and also is shrinking marine ecosystems. Warming has also been associated with increased stratification in the surface ocean, which should expand the size of marine dead zones, which I'm showing here in this map. So although this is an increasingly important problem, the processes that contribute to ocean deoxygenation and how these processes will change in the future is still uncertain. And so that brings us to past ocean anoxic events, or OAEs. And so these past events of ocean deoxygenation are typically associated with warming of the climate, sea level rise, and even mass extinctions. And so this figure shows commonly studied OAEs over the past 500 million years. And from this plot, we can see that local valleys in dissolved oxygen typically coincide with local peaks in temperature in the ocean. And this figure also demonstrates that most of the well-studied OAEs all occurred in a background greenhouse climate state. And so the CO2 levels are much larger or much greater than the typical of a Cenozoic icehouse state. So that brings us to the Earth's penultimate icehouse, or the Late Paleozoic Ice Age, which spanned from about 340 to 285 million years ago. And during this time period, we experienced CO2 levels that are more comparable to the Cenozoic glacial state. We also experienced oxygen levels that were some of the highest for the Phanerozoic. But amidst these extremely high oxygen levels, there is evidence for an ocean anoxic event during this time period. And so before getting into the geologic evidence for this OAE, I just want to give some context for the late Paleozoic world. So the specific interval that we are interested in is during the late Pennsylvanian. And so here I'm showing a paleogeographic reconstruction from about 300 million years ago. You can see that the supercontinent Pangaea was assembled, and also there were actually multiple ice sheets in southern Gondwana that waxed and waned with glacial and interglacial cycles during this time period. Also, the ocean basins look very different during this time. The Panthelastic Ocean covered an entire hemisphere of the Earth. And also the Paleotethys Ocean is the other ocean basin, which is situated between Euramerica. And here in NCAR, we would be on this little tropical island. And it's then situated by these are called the China blocks, or a Cathasian Peninsula. So during the late Pennsylvanian, there was a warming event over the Kazimovian-Gazelian boundary, or the KGB, at about 304 million years ago. And so leading up to this interval, here is a figure of a CO2 reconstruction, and you can see the details of it in Ritchie et al. 2020. It's based on stomata and paleosol data. And leading up to this KGB interval, we can see these glacial, interglacial fluctuations in CO2 on the order of about 400,000 years. Then, right before the KGB, there is an abrupt rise in CO2 from 350 to about 700 parts per million over about 300,000 years. This abrupt rise in CO2, which is in excess of the typical interglacial range, also coincides with negative excursions in Delta 13C and Delta 18O, which support a coincident rise in sea temperature, and also a perturbation to the global carbon cycle, as well as a sea level rise and a loss of marine biodiversity, which is seen globally. Before getting into the evidence for deoxygenation, I just want to show you the location of the records that were analyzed for this study. This is the location in South China, which essentially sits on the border of the Paleotethys and the Panthelastic Ocean. And so there's evidence that this warming across the KGB was coupled with marine anoxia. And so for this study, a few records were looked at, but I'm just showing one here from South China, where there's a paired uranium and carbon negative isotope excursions. And so uranium is a common proxy used to reconstruct redox conditions in the oceans, and a negative uranium excursion supports expanded marine anoxia. These records were also used to inform carbon cycle modeling with LOSCAR and uranium mass balance modeling. And without getting into the details of that modeling here, I'll just say that that modeling supports a 9,000 gigaton injection of organic matter derived carbon over 300,000 years, and also a 24% increase in the extent of anoxic seafloor area. And at this point, the actual source of the carbon injection is uncertain. It could have been associated with methane from a large igneous province, or it could have been melting permafrost, but the exact source is uncertain. The next sort of question associated with this interval is why did this carbon injection lead to ocean deoxygenation during the interval? And so that was my contribution to this study, was to start using climate model simulations using the fully coupled community Earth system model version 1.2. And so I compared two different simulations. The boundary conditions differ with respect to CO2, sea level, and high latitude ice sheets. So essentially the two simulations are a glacial and an interglacial state over the late Pennsylvanian. But in the low CO2 case, which has 280 ppm CO2, there's relatively lower sea level and expanded ice sheets shown here with crosshatched areas. And in the high CO2 case, there's 560 ppm CO2 with relatively higher sea level and reduced high latitude ice sheets. We ran these simulations at about 1 degree resolution in the ocean, and they're run for about 2,500 years, such that the deep ocean reaches quasi-equilibrium. So the first sort of mechanism that we found that was plausible was enhanced upper ocean stratification with warming would have led to decreased oxygenation of the surface ocean. So here is a zonal mean plot of density and temperature in the upper 500 meters of the Panthelastic Ocean. We can see that in the high CO2 simulation, there is a poleward migration of those isopycnals, supporting increased upper ocean stratification. Both a strengthening of the surface halocline and a shoaling of the thermocline both support this stratification and inhibit convection and likely inhibit ventilation in the upper ocean. The second mechanism we found to support oxygen loss was a stopping of deep water formation in the northern Panthelastic Ocean with warming. So here I'm showing global maps of the climatological maximum mixed layer depth. So essentially that is taking the maximum mixed layer depth of every ocean grid cell across the whole year. And we find that in the high latitudes, these maximum mixed layer depths occur in the cooler winter and spring months. And so in the low CO2 simulation, we see very high mixed layer depths supporting deep convection in both hemispheres. And then in the high CO2 simulation, we only see these large mixed layer depths in the southern hemisphere. The sort of result of these differences in deep convection causes a global reorganization of meridional overturning circulation. So in the low CO2 and high CO2 simulations, we see a descending branch in the southern hemisphere. In the high CO2 simulation, this branch completes to form one large overturning cell, essentially, in the Panthelastic Ocean. Whereas in the low CO2 simulation, there's also a relatively weaker descending branch in the northern Panthelastic Ocean. So this supports ventilation of deep waters in both hemispheres. Why do these differences occur in the meridional overturning circulation? Well, here I'm showing you polar plots of the northern hemisphere. And so here we can see that relatively lower sea surface temperatures near the North Pole in the low CO2 simulation support widespread sea ice formation, sort of an island of sea ice forms. Whereas in the high CO2 simulation, sea surface temperatures never reach values low enough to support sea ice formation. And so the seasonal brine rejection that occurs with the growth of this sea ice actually increases sea surface salinity, lowers the buoyancy of the surface, and supports deep water formation in the low CO2 case. Whereas in the high CO2 case, the surface is too buoyant and deep water formation never occurs. So I just want to point out that one caveat to these simulations is that they do not have active biogeochemistry. And so instead of being able to look at direct dissolved oxygen content in the simulations at this time, we could sort of start to look at ventilation of deep ocean masses, looking at the ideal age tracer in CESM, which tracks time since the water mass has been in contact with the surface. And the idealized age of water masses has been seen in other paleoceanographic simulations to correlate with dissolved oxygen in the deep, though this is an indirect comparison. But essentially, what we see in these simulations now is that the ventilation and deep water formation occurring in both hemispheres is supported by these ideal aged. We see this seems to support well-ventilated deep waters in both hemispheres in the low CO2 case, whereas in the high CO2 case, we see sort of these very old waters accumulating in the northern hemisphere, suggesting there is poor ventilation in the northern hemisphere. But then again, dissolved oxygen is complicated, and so further simulations with active biogeochemistry should be run. So just for some conclusions, the Casimovian-Gazelian boundary at about 304 million years ago was a warming event that we think led to widespread marine anoxia and can provide useful insight for warming-induced ocean deoxygenation in an icehouse climate compared to other OEEs that occurred in a background greenhouse climate state. Two plausible mechanisms for ocean deoxygenation are increased upper ocean stratification and also a slowing of meridional overturning circulation in the northern hemisphere. And lastly, thank you for listening. And I just want to again acknowledge my collaborators. And if you would like to contact me, feel free to reach me at any of these places.
Thank you for the excellent talk. Are there any questions? So I was wondering, whether you are able to, I know you need to have the full geochemistry in order to determine the oxygen concentration in the deep sea. But I think one thing you can start to do, which is very easy, is just to plot the solubility pump. So the idealized age somehow determines the biological pump, and then the solubility pump, you can at least see how much the oxygen will be reduced. And I'm happy to give you a program which you can just diagnostically run in order to determine the saturation rate, or you can just ask Keith Lindsay, probably has such a program too.
Okay, thank you. I'll definitely reach out to get that code.
Yep.
Thank you.
More questions? Fortuna.
Yeah, thanks. Well, I have one question. Very nice talk. I was wondering about transient versus steady state. As in sort of global warming simulations with our remake, we found that sort of with warming, there is this stratification and the overturning circulation slows down and then oxygen decreases. But then at the end, at equilibrium, oxygen increases again due to, well, as the overturning circulation resumed, and then the oxygenation is more caused by the temperature and solubility mechanism, but less so by water mass age. So I'm wondering, how long did you carry out your runs, and did you reach equilibrium, or are they still sort of transient staged?
We ran the simulations for 2,500 years each. And so the end goal, we stopped the simulations because the deep ocean temperatures and salinity were steady. And so I would consider these in quasi-equilibrium.
Okay.
I think that time scale is consistent what we run with coarser resolution runs and what we see also in the 1 degree resolution. I mean, it's not perfect, you need to run longer, but I think there's computer cost to consider too, and I think that's probably a good first approximation.
Yeah, and we also have the oxygen isotope. We have the water, the isotope enabled component in these simulations too, so they were getting expensive.
Okay, if there are more questions, thank you very much. And if there are more questions, you may want to go to the chat to address them. And then the next speaker we have is Esther, presenting the Paleo Working Group updates and plans for the future 2021 and 2022.
Thank you, Arnie. Let me share my screen here. I don't see it. Yeah. Okay, hold on. Did I share? Okay, what is going on? Let's see. Let me try this.
Yeah, that works.
That works? Okay. Do you see my, oh, nope, sorry.
These are the
wrong one.
Yeah, the wrong file, yeah.
Yeah, let me get this one up. It's probably the problem. Oh wait, wrong again, sorry. Yes. Okay, now I think we're there. Okay, and do you see my screen?
Yes, I see that now. Yeah.
Okay, good. Whoop. Okay, so yeah, I just have a few slides to update you on our recent activities and our plans for the next 2 years with our new CSL allocation. And I just want to acknowledge my co-chair, Arnie Winguth, for his help, and also Betty Otto-Bliesner, lead in the Paleoclimate Group, for their contributions with the Paleo Working Group activities. Okay. with all my windows, it's really hard for me to see my screen. But yeah, the first slide here lists our recent activities and accomplishments I want to let you all know about. First, that we've completed some CMIP6, PMIP4 Tier 1 simulations with the CESM2, and the data is now available for these on the Earth System Grid Federation. These simulations are the mid-Holocene, the last interglacial 127K, and the mid-Pliocene simulation. These were run at the FV 1x1 resolution. And then we also have another CMIP6 simulation, the last millennium, run at the FV 2x1 with the WACOM 6 atmospheric component coupled to CESM2. And this data will eventually be made available. It's not available yet. These simulations have been documented in some publications for the CSM2 AGU special issue. Ren Feng has documented the PLIOMIP2 mid-Pliocene simulation in James. This paper also compares the earlier versions of CESM, also run with the PLIOMIP2 simulations, boundary conditions. There's a paper by Betty Otto-Bliesner in Paleooceanography and Paleoclimatology, documenting the CESM2 mid-Holocene and last interglacial simulations. And then Zhang Zhu has a recent paper in GRL documenting his work with CESM2, simulating the LGM with the CAM6 and CAM5 versions of the atmosphere model, and he gave his presentation yesterday on this work. We also have a number of contributions to the PMIP4 special issue in climates of the past. The Betty Otto-Bliesner has led a paper for the intermodal comparison, intercomparison for the LIG 127K simulation. And then there's other model intercomparison papers as well with our simulations involved. And then lastly, I just want to let you know that the PLIOMIP2 simulation run with the CESM2 that's available, the PLIOMIP2 simulation run with the earlier versions of the CESM is also available at this website here. Okay, that did not advance. There we go. I also want to let you know that the iTrace project, which is an NSF-funded project to look at and simulate the transient climate evolution during the last deglacial period from 20,000 years ago to 11,000 years ago, with the isotope-enabled CESM 1.3 version, will soon be available, and we now have a first paper out in Science Advances documenting that. This was a project led by Betty Otto-Bliesner and Zhengyu Liu at Ohio State University. Elias Summers also presented on a new work that is a project developed jointly with the Land Ice Working Group and the Paleoclimate Working Group to simulate transient ice sheet climate evolution over the last interglacial period. And that has a paper in preparation, and you can check out her presentation that she made during the joint Paleoclimate Land Ice Working Group meeting last week. And then we have some work that was done at the University of Michigan. And there's some papers led by Zhang Zhu, who's now a new project scientist here at NCAR, looking at warm climate simulations run with CESM2 a paper exploring state dependence of equilibrium climate sensitivity with CAM coupled to the slab ocean model. And then also a couple of papers documenting a deep MIP simulation for the Eocene. And you can check these out and contact these authors if you're interested. And then we have been working lately on applying new CSM configurations to simulate multi-millennial transient, long transient climate simulations. In particular, we have 2 configurations that we're exploring. The first is using CESM2 coupled to the CAM-Chem version, the tropospheric chemistry version, to look at the response to volcanic aerosol emissions over the transient Holocene, as well as the other forecanes. And then we have another project with CSM2 coupled to the ice sheet model, CESM2, to look at transient climate ice sheet evolution over the Holocene. And you should be hearing, hopefully, more about these 2 projects in the next couple of years. Okay, next I'd like to just let you know what we're doing, what we have planned to do for our next CSL allocation that started in November. This kind of falls into 2 categories. The first is plans for expanding capabilities for paleoclimate applications. And then the second is to provide new science and high value community simulations. In particular, for expanding capabilities, we are planning to test the lower resolution of the CESM2 coupled to the ice sheet model to be able to simulate long multi-millennial transient simulations and explore different acceleration and spin-up techniques. Then we are, there's a large amount of computer time for investigating the state dependence of cloud feedbacks in the CAM parameter space. And this is a study that will be led by Jean Zhu in collaboration with members of the Atmospheric Model Working Group. We're hoping that with using paleo constraints from paleo data, we'll be able to help guide choice of model parameters going forward. We're planning to enable and test the suite of geotracers available and continue implementing water and carbon isotopes in all components of CESM2 and continue development into the development stream of CESM3. And lastly, towards the end of this time period, maybe the second half of 2022, we plan on testing the development version of CESM with the MOM6 ocean model, which has been chosen for CESM3 for a paleoclimate. In particular, we're targeting the last glacial maximum because it's a challenging time period to simulate with CESM. And then for new science and to provide some high value community simulations, we have a large amount of computer time devoted to some high resolution CAM paleoclimate simulations. This was something that we heard last summer that the community was interested in having available. And we feel it's time for this, where we can, with now these would be CAM only simulations run with boundary conditions from some of the time periods that have been simulated in a couple mode with CESM2, for example, the LGM, and some extreme warm past climates like the mid-Pliocene, the early Eocene. And these are ideal for proxy data comparisons, looking at weather extremes, atmospheric rivers, tropical cyclones, et cetera. We also would like to continue to work with CESM2 coupled to WACM for paleoclimates, in particular the LGM and the mid-Pliocene seem to be good targets for this. These would be equilibrium type simulations. And then, as I mentioned before, we have been working with the CESM2 coupled to the ice sheet model, and we have 2 long transient multi-millennial simulations planned for this. These would be for periods of major ice sheet retreat and regrowth. One is the end of the last interglacial period to glacial inception, and the other is the transient Holocene. And these 2 simulations are shared jointly with the Land Ice Working Group. And lastly, we have some time that we'd like to devote to investigating potential tipping points in the Earth system, looking at the response and feedbacks to meltwater during abrupt cold events of identified in the past climate reconstruction, such as the Heinrich Stadial 11 event before the last interglacial period and the 8.2K event in the Holocene. Okay, and lastly, before I put up some topics for discussion, I'd like to let you know that we are in the process of updating our Paleoclimate Working Group webpage to facilitate better communication with the community and kind of provide some improvements on and updates on our activities. So this is what you'll see when you go to the working group webpage. To the left, you'll come to this blurb, and below that figure are new links for finding what are the recent and notable NCAR simulations that we have information on and provide output for. Also our past simulations that people may still be interested in, and these would be organized by model version. And then any other notable simulations that are available to the community, such as the PLIAMIP2 multi-version ensemble that is documented in that paper by Ren Feng. And then below that, we would like to see if people are interested in the community to having some links to their own work. Once they're made available to the public and papers are written, we can envision seeing some links from interested community members so that we can highlight work that the community is doing. And the community is doing such great work that I think we ought to highlight it, and people out there interested in using CESM for paleoclimate will be able to find what's happening, what are people doing. So this is obviously going to be something that is up to the individual community member to decide if they want to add to our community highlights here. Below that, we have always had a link to some paleo resources, but we're going to try and get it front and center so that people can find out where to go to find information on setup and analysis tools and model codes, other codes, comp sets, and recipes for setting up different paleoclimate simulations. Right now, most of what we have on this webpage is related to CESM 1.2, and we'd like to get it updated to CESM 2. And also this, we see this as a way for the community to contribute. So if anyone has any neat analysis tools or recipes for a particular period, they can contribute to this paleo resources page. And then we'll have some other information such as links to the CSL proposals so you can find out what we are planning currently, what we're working on now. So, and then oh gosh, come to the end of my talk. I'm happy to take questions before we get to our discussion.
Thank you, Esther. Are there any questions from the community?
I'm going to stop my share because it's really hard for me to see everything happening on my little laptop screen. Okay.
Are there any questions? Maybe any questions? I don't see currently any. Oh, there's Betty. Betty, you wanna?
I just want to re-emphasize what Esther said. We'd really like to bring the community together to make this a Paleoclimate Working Group for the community. And I think it's really important now because, as you saw yesterday and today, there are a lot of you in the community that are using some version of CESM. And it would be great to, of course, it's up to you, and I can put in a link of what you might provide if you want to have us put a link to your simulation on the page. But it'll be up to you. You'll be responsible for the data, and you'll also be responsible for interacting with community users. And it's a great way to advertise what you've done, because there's, from last millennium to very deep time, there's a lot being done. And so I just want to emphasize again, we want this to become a community working group.
Betty, I do have a question actually regarding that. And so for the data, these are large amount of data. They're normally time limited with the NSF project. So the data storage goes away. So it would be good maybe for some key paleo simulation that in the next allocation you ask for more, or we could ask for more storage, so that the Paleo Working Group would have the capability to store some of these simulation, because that's always the great challenge, is to find actually a unique storage place. If we have these huge simulation, we are running often out of storage. And so maybe it's worth to request that with the next CHAP meeting, so to have a larger allocation space.
Yeah, you're right. Storage is a challenge. It's a challenge even for us to be able to.
Big challenge.
We're right now transferring things from the HPSS, which is going away this fall, and making sure we keep key simulations, maybe not keep things that are over there that we don't need, like restart files for CCSM3. But yeah, it'd be interesting to hear if there are comments from the community on other options besides NCAR, because I admit it's a challenge and there's some restrictions on how much we can bring in that wasn't done by on our CSL allocation. It may be a discussion with NSF too. They really need to think about this. But.
Yeah. Okay. If there are no, Betty, yeah, you still have your hand raised, Betty. Okay. Okay, I guess I can put up a slide that can help guide our discussion, which we will have next. If I can try and do this. All right. I'm going to try this again. Share screen. Yeah. Okay. Okay, I hope everyone can stay around for a bit of discussion. We can talk about how we might work as a community to what simulations the community would like to see done, how we might better